So we did one problem finding the volume. Well, no, not finding the volume. This is actually finding really the mass, which is actually what we're going to do in the next section, mass calculations. And well, so okay, so the trick to go about, or rather the process for the whole thing is, number one, what the limits of integration in the original integral in rectangular are telling us. Well, that's going to give us an idea of the region over we're going to integrate. And then from there, well, we also need to look at the projection in two dimensions. That way we can get the limits of integration between x and y for the remaining two integrals. So really the 3D part, which is given by the innermost integral in the triple integral, that's those are the limits over the variable z. All right. So and well, the thing is here, so you really have to convert the coordinates, because even if you attempt to evaluate the integral in rectangular coordinates, it's impossible, because, for example, try to do a u substitution for z, and we already did it actually. So u would be x squared plus y squared plus z squared, so the derivative would be 2z, so we would be missing a factor of a z right here that stands the u du part of the problem. So in this case it's impossible to evaluate the integral using, well, no, actually it's not impossible. You know what? You could do a trigonometric substitution like the ones we learned back in calculus 2, but actually taking x squared and y squared as constants, that whole thing, call it, maybe some c squared, so you would have the form c squared plus z squared, and you can use the arctangent substitution. Well, that would be a clever way to go about the integration if we used trigonometric substitution. But I mean, that'll be too exhausting to do. I mean, it would be a good practice to go back to trigonometric substitution. Why not? And it would be great to do a trigonometric substitution involving 3 variables. That'll look cool. But I mean, that's the reason why we have spherical coordinates, right? To make our job a lot easier. I mean, it's a number of lines, but these integrals that we have are very straightforward integrals. Nothing, not even a u substitution here, all right? So let's look at one more example. So use spherical coordinates to write the triple integral that represents the volume of the solid region R, bounded below by the cone z equals x squared, the square root of x squared plus y squared, and above by the hemisphere z equals to the square root of 16 minus x squared minus y squared. So notice hemisphere, it's only the upper part, but in this case it's going to be bounded by the solid will essentially look like this. So number one, let's draw a Cartesian, well, not plane, rather a Cartesian space. And well, let me highlight this using so let's highlight the cone. Highlight the cone. That's going to be, I'm going to draw using the same color. Well, the cone is going to look like this. Alright. And well, above the cone we have a hemisphere, or only part of the hemisphere, because that whole sphere, if we take the sphere as a whole, it would essentially look like this. But we don't want that whole sphere. Well, it's kind of hard to draw the hemisphere, but in this case, the way I'm going to draw this, it's only the part that looks spherical in this case, and it's gonna look like an ice cream actually. All right. So what do we have when we go to the mall? We get an ice cream, or we have a cone, and well, in this case, the scoop of the ice cream is sort of half of a sphere, right? Unless you get like 2 or 3 scoops, right? But well, in general, that's the volume that we're going to find. Well, we're going to set up the integral that finds that volume of a cone. And and the part of the sphere. All right. So let's see. Number one. Well, that's the 3D part of the problem, the picture in 3D. And well, so we need to understand what's going on in the 2D plane, that is the XY plane, which in this case, it will be the projection of this. And in this case, we get that by finding the intersection between the surfaces, because, I mean, look at the outermost at the points that lie on the outermost solid region. I mean, they would be on this circle right here. And well, if we project this towards the XY plane, this should look like this. Well, there has to be some circle. What's the radius and what's the equation of the circle? Well, it's going to be the circle or the circular trace, which is the intersection between this part of this upper sphere and that cone. So to get that, we will set both equations together. So in this case, z equals to z, that is the square root of x squared plus y squared, equals to the square root of 16 minus x squared plus y squared, minus, and we'll square both sides. X squared plus y squared equals 16 minus x squared plus y squared, and we'll have all the x's and y's on the left hand side and the constant on the right hand side. That's going to be 2x squared plus 2y squared equals 16. Divide both sides by 2 to simplify the equation. That should give us x squared plus y squared equals to 8. So yes, we have this circle right here. I think it's consistent with our initial, projection, right? So, what's the radius r for? So number one, how about, so from here, r squared equals 8, r, it's the square root of 8, which is really 2 root of 2. So we got something already. Let's see. Let's see, what are we going to have over here? All right. So, so when we set these equations together, so what's going on at the boundary? Well, number one, let's start converting all to spherical coordinates. I'm going to start with this. So this means z squared equals to 16 minus x squared minus y squared, and x squared plus y squared plus z squared equals to 16. Well, the sum of the squares of x, y, and z is really rho squared. That means rho equals to 4. So we already have some of the limits for the triple integral for rho in particular. Well, so let's see, at the boundaries, this is what's going on at the boundary. So what's the height? What's the height exactly at the boundary? Well, that's actually the intersection between the two surfaces. Z equals to square root of 8. Well, so in this case, we know some of the relations from the conversions of coordinates. We know that Z equals to rho cosine phi. Actually, I'm going to say theta, but it's actually phi. That means Z, which is the square root of 8, and rho, which is our radius, the radius of the sphere. Careful, remember that there's really two radii involved when it comes to describing a sphere. The radius r, which is on the which is located in the projection onto the xy plane, and rho, which is really the radius of the sphere that is in 3D. So that's a 4 cosine phi, and cosine phi equals to square root of 8 over 4, which we can simplify very nicely, you'll see. So the square root of 8, which is, okay, it's 2 root of 2 over 4. That's cosine phi equals root of 2 over 2. And well, we can find out what the angle phi will be at the point, at the boundary right here. So what we're doing here is finding what's this angle rho, the one that varies between 0 and pi, starting from the positive z-axis and ending in the negative z-axis. So well, v will be the arc cosine of root of 2 over 2, and in this case this is pi over 4. So what do we have? We have a cone that has an angle of 45 degrees with the positive z-axis. So that means our overall cone, so we're going to have like a cone like this. Can you imagine an ice cream with a cone 90 degrees? That's a lot of ice cream, right? Wow. And well, so that's well, of course that's going to vary from 0 to pi over 4. And well, so that's what this equation is going to tell us. So let's gather all the information. So number 1, so rho varies between 0 and 4. That is because that's a sphere of radius 4. And what else? Phi varies between 0 and pi over 4. And lastly, theta varies between 0 and 2 pi. Yeah. Because in this case, check the projection. The projection involves the whole circle. I mean, unless you cut your ice cream exactly in half in the middle. That's kind of weird, right? So let's set up the integral. So the integral for volume, well, in general, number 1, volume equals the triple integral over the region R dv, and that triple integral represents volume again as long as the integrand it's only the number 1. All right. Well, we need to convert this to spherical coordinates. Recall that dv number 1 is dz, dy, dx, or your favorite order. Well, not necessarily your favorite. I mean, the one that is easier to set based on the complexity of the integral that this gives rise to. However, recall that the dv or the dx or the dz, dy, dx in Cartesian becomes it becomes rho squared sine phi d rho d phi d theta. So let's put the limits of integration that we had over here. Well, rho again varies between 0 and 4. Phi varies between 0 and pi over 4. And theta varies between 0 and 2 pi. And that's the integral that will calculate the volume for us. All right. And well, in this case, we're just setting up the integral. We're not evaluating. So this is more or less how the questions on the exam are going to look like. Just set up the integral. Do not even evaluate. And again, all we need to understand is why or what's going on in 3D, what's going on in 2D for the two outermost integrals. Kyle?
At the boundary section, how did you know that z was your rate?
Which one?
At the top when we were doing the at the boundary, right?
Oh yes, because so it's the intersection. Well, this boundary right here is the height z where the sphere and the cone intersect. So that's the the intersection in this case. Well, some observations here. Sometimes when we want to convert equations from the Cartesian system to the spherical system in this case that we're working on. So this equation z, which is the equation of a cone, we can always simply say that phi equals to pi over 4. And well, a hemisphere, we can always say that rho equals to 4. Well, how can we just denote these equations in Cartesian directly to the spherical coordinate system? Well, okay, let's go to the animation again.